Welcome, ladies and gentlemen. So I'm going to go ahead and ask for the generalized form of e to the x, our known Maclaurin, right, familiar function. And then we're going to go ahead and use substitution to generate a new Maclaurin series for e to the negative x squared. And so we can start with our known Maclaurin. We know that e to the x is given by, what, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus plus. And how could we generalize that term? What would that look like, Vivian? Awesome. Thank you. And so if we wrote the Maclaurin representation as a series, right, we could just write our summation notation from n equals 0 to infinity of this generalized nth term, but it'll be useful to expand it as well. All right, so now we want the Maclaurin for a new function, e to the negative x squared. No problem. We've seen in the past how we can use substitution as a strategy for rewriting my known Maclaurin, right, to generate the Maclaurin for a new function. So we're going to go ahead and rewrite the same exact thing, but it's going to be e to the negative x squared instead of e to the x. And so we'll go ahead and make that substitution. Everywhere we see an x, we'll just simply plug that in. We're on a roll here. And what do I need? I still need a squared over the 2 factorial and a cube. What are we substituting in? Opposite of x squared. So this becomes negative x squared, negative x squared, negative x squared. It's that easy. And let's see what that does for us. So our signs now looks like our even exponents, right, are going to take that negative times a negative and make them positive terms. But our odd exponents are going to keep a negative. So we've taken, right, a non-negative series with, a series with non-negative terms and changed it into an alternating series, right? You guys see that? All right. So this becomes 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus generalized term becomes negative 1 to the n over n factorial, and this becomes x to the 2n. Is that what you guys got? X to the 2n? Awesome. And sometimes you'll see that, you know, the fraction with the n factorial up front and then x to the 2n on the ground floor, depending upon how the text writes it. So I'd ask at this time that you raise your hand if you had this last generalized term. Yes? Good job, you guys. And we could write that with some summation notation if we so choose. I'm going to go ahead and just squiggle underline it. I feel like we've done a good job generating. Okay, so Tyler asked last week, and I just want to reiterate, we do have to memorize the common Maclaurin series for e to the x, sine of x, and cosine of x. Now we've got those other ones in there too that we've worked with, like ln of 1 plus x, but those aren't the big three. The big three are the e to the x, sine of x, and cosine of x. All right, and we'll be using that table actually from your text today. Use the second order Maclaurin polynomial for f of x equals cosine of x, which ends up being the same as the third order Taylor polynomial, and use it to approximate cosine of 0.2. Remember, a Taylor polynomial centered at x equals 0 can also be called a Maclaurin polynomial. So let's go ahead and use my p sub 2 of x. We know that that's just the x squared, right? My Taylor polynomial that goes to the x squared term. And with cosine, that's the one that starts at 1 minus x squared over 2 factorial. So this is just 1 minus x squared over 2. Raise your hand if you had the same second order Taylor polynomial. Yes? Good? Okay, so now we'll use it to approximate cosine of 0.2. Well, that's as easy as plugging in 0.2 to my Taylor polynomial. And it looks like if we do that, we get 0.04 or 0.02, 1 minus 0.02. 0.98. So raise your hand if you generated 0.98 for your approximation. Yes? Cool. All right, so the question is, what's the maximum error for that approximation? And we can do this a couple different ways. We saw from last class discussion with our error bound, right? Bounding the error from a Taylor polynomial approximation, that if we have an alternating series, that is, if my terms, right, alternate in sign, if they decrease in magnitude, and if the limit of the nth term goes to 0 as n goes to infinity, then we know the maximum error from such an approximation is given by the magnitude of the next term, right, evaluated at my x. And so I know that my maximum error in this case is less than or equal to the value of the a sub n plus 1th term, right? I just have to go to the next term. Because this was a second order, right, we would first go to the third order. But the third order we saw has a 0 coefficient, so that won't do us any good. We need to go one more. We need to go to the 4th degree term. That's okay. I know the next term in this cosine series will be plus x to the 4th over 4. So I know my maximum error. Let me just add that this is an alternating series test. And that. This is really called the alternating series error bound. And we know that that is given by, at most, the magnitude of the next term evaluated at my x. And that equals x to the 4th over 4 factorial, evaluated at 0.2. And that equals what? 6.66 repeating times 10 to the, you guys get -5 for your exponent, -5? Okay. So, we expect our approximation of 0.98 to be within, right, within 0.000040666666, right, of the true value of cosine of 0.2. To show this visually, we could go ahead and compare the error bound with the predicted error from our calculator. So we could go ahead and construct a graph by using our absolute value, right, the magnitude of the difference between the exact function cosine of x and our second order Maclaurin polynomial, the 1 minus x squared over 2, and then we'll go ahead and make our y window 0 to our maximum error. What's our maximum error? Very small rocks. The idea is that our graph of the error in our approximation should stay within, right, that y scale maximum. So let's go ahead and take a look at that visually. This is pretty cool. So we'll go ahead and take our y equals, and we'll enter our true function. That is cosine of x exact. Then we'll enter our second order Maclaurin polynomial for cosine, and that is 1 minus x squared over 2. Then we'll go ahead and enter our error function. We know our error function is the magnitude of the difference between those function values. That is exact function value minus our approximate function value. So how would I do that? Math, num, abs, y1, so that comes from bars, y bars, function, working out, Tyler, eating eggs, protein, complete protein, nature's complete protein. y1 minus bars, y bars, function, y2. All right, and so now what I want to do is go ahead and turn off the graphs of 1 and 2. You can't delete them, right? Otherwise, we won't get a third function generated, but I want to go ahead and toggle them off so they're not producing a picture, right? And so we've gone ahead and used y1 and y2 to create my error function, absolute value of y1 minus y2, and we're going to set our window up to be our error. And so where did we set our approximation? Our approximation was Maclaurin, so it's centered about x equals 0, and we went to the x value of 0.2, so I'm going to go from negative 0.2 to positive 0.2 for my x window. And for my y window, I'm going to go from 0 to, and what was my error bound? My maximum error was what? it's 6.66666 to the, so times 10 to the, times 10 to the negative 5. So I'm going to actually set my y scale to that maximum error bound. Now, visually, if we've done this correctly, and that is in fact the maximum error bound, our error, right, should stay within that y maximum, right, in the interval negative 0.2 to positive 0.2. Let's see if that's the case. So here we go with our graph, and we see right there, as we get towards the edge, we're getting right close to that maximum error, which, of course, is very small. I mean, it's 6.66 times 10 to the negative fifth. But we could do, oh, look at that. We could do a quick verification by doing trace. And we'll enter our x value, right, our x value of 0.2. And now I don't want that. Can I do trace and pick? I can't pick. Oh, no, we want the error. So I want the error when x equals 0.2. And let's see what the actual error is. 6.6578 times 10 to the negative fifth. So were we within our predicted error? Yes. Right? We were within our absolute maximum error. That's pretty sweet. Nice. And so our error was less than our 6.66 times 10 to the negative fifth. That's pretty cool. All right, so what kinds of questions are you having about our Taylor polynomial approximations and our maximum error? In my opinion, the alternating series error bound is easier, right, than the Lagrange error bound. The Lagrange error bound, however, right, will work for any series, right, with the Taylor polynomial approximation, not just an alternating series. And so in that respect, it's more powerful. All right, let's go ahead and pause the recording then and take care of our housekeeping. All right. So we know that the general form of a function, right, written in terms of its nth order polynomial and remainder, is simply given by f of x equals our Taylor polynomial, our nth order Taylor polynomial, call it p sub n of x, and then plus the remainder function, right, r sub n of x. Wherever we stop our Taylor polynomial approximation at whatever order, the remaining portion of the series, this remainder function, is my error, right, in the approximation from my Taylor polynomial p. Together, those are equal to my original function f of x over the interval of convergence. So what's the error from that nth order Taylor polynomial? Well, we saw if f is given by p sub n of x, and I give you this one, right? So p sub n of x plus r sub n of x, then my error, that is the magnitude between the actual function value and my nth order Taylor polynomial predicted function value, is simply the absolute value of my remainder function, right? R sub n of x. And so if I subtracted over the p sub n of x and took its magnitude for absolute value, that would give me the magnitude of my remainder function. Uh-oh. Based on. Okay. So we saw how this magnitude is guaranteed to be less than or equal to the maximum value attained by my next order derivative over n plus 1 factorial, and then times the next term in my Taylor polynomial, that is x minus a to the n plus 1, right? Or simply rewritten with m being the maximum value that's produced by that derivative. Where m is the maximum value of the n plus first derivative attained on the interval between x and a. The thing is that can be kind of sticky because we have to, through inspection, sometimes say, how could we maximize the value of that derivative, right, based on the interval in which we're looking. That might purposely include picking an x value so that we can make that derivative as big as possible, just to guarantee that our error is within that bound. We saw the alternating series bound. From our Bellwork, we know that if we have a a series where the terms alternate in sign. The magnitude of the terms decrease in value. And the limit of the nth term goes to 0. As n goes to infinity, then we can apply the alternating series error bound. The truncation error after n terms is less than the absolute value of the n plus first term. That is to say, the error is at most, right, the magnitude of the a sub n plus first term. Okay, so basically that was all for Sydney. You're welcome. That's what we did last time. So we developed a way where we could bound the error from our Taylor polynomial approximation. And now we're going to go ahead and move forward. So here's our error. It's given exactly by the n plus first derivative, right? Evaluated x equals c for some c in between x and a, and then the magnitude of the next term, right? The thing is that we don't know necessarily what that c is. And so even though this formula is super powerful and tells us exactly, right, it's exactly equal to this, we typically try and choose the largest value of this derivative and then just bound the error by saying it's less than or equal to that maximum produced. All right, so let's go ahead and do one more together, and then we're going to shift our gears to find out about convergence versus divergence. So suppose the second order Taylor polynomial for f of x about x equals 2 is used to approximate f of x, and suppose that the third derivative of x, the magnitude of that third derivative is less than 2.3 for all x in the interval 2 to 2.5. Show that the absolute value of f of x minus p sub 2 of x, what's that? Well, this looks like my error, right? This looks like my error. Right, that's the error in my approximation, is less than 0.05 units for all x on the interval 2 to 2.5. Can we use the alternating series error bound? Are we given any indication that the terms alternating sign, decrease in magnitude, or approach 0? No. And so we don't have enough information to apply the alternating series error bound. We don't know that we have an alternating series or not, let alone whether or not the terms decrease in magnitude or go to 0 as n goes to infinity. But we do have a lot of information right around this second order Taylor polynomial. We've got the third derivative's magnitude is less than 2.3. So I think that we can take our error, which equals our remainder function, and we can bound it by saying that's less than or equal to, right, the absolute value of the next order derivative would be the third derivative, evaluated at some x equals c in between my approximation x equals 2 and my x values, right? Looks like it starts at 2 and then goes to 2.5 times the next term would be x minus, where is it centered? 2, so x minus 2 to the, and this would be the third, over 3 factorial. Which in turn is equal to, well, our third derivative magnitude, we're told, is less than 2.3. So this becomes as easy as plugging in 2.3 here. Our 3 factorial is a constant. The only thing we're stuck with figuring out is this next power term, right? The third degree term after that, the second order Taylor polynomial. And so my third degree term, right, could change in size depending upon where I'm looking in my interval. My interval spans from what? 2 to 2.5? Right, our interval goes from 2 to 2.5. This term is maximized when x equals what? 2? No. What? 2.5. And so this is a case where through inspection we have to pick x to be 2.5 so that this term's magnitude is maximized so that we're guaranteed to be within, right? Within this maximum error achievable. So that will bound our error. We know then our approximation is guaranteed to be less than this number. If we didn't choose 2.5, then our error wouldn't be guaranteed to be less than this approximation for the entire interval. It might work for 2.1, it might work for 2.2, right? But by purposely choosing x to be 2.5, we're guaranteeing that our approximation is less than or equal to this value. So we're going to choose x to be 2.5. We did this on our own, right? We picked that on our own through inspection. But now we're guaranteed to be less than this, so it looks like we can now just get that. And can I put it all in at once? I'm going to try. So it looks like 2.3, and that would be 0.5. And divided by, and that'll be 3 factorial. How do we do? That looks big. Did you guys get that? You guys got that. So 2.3 times 2.5 minus 2. That's 0.5 cubed all over 3 factorial 6. Okay, so our approximation, actually that interval is pretty big though, 2 to 2.5. So our approximation is guaranteed to be, oh, that is less than 0.05. And so we have shown that we're less than the 5/100ths. So I'm feeling pretty good about that. So 0.0479. And that is less than the 0.05 as desired. Sweet. All right. What questions do you guys have about our Lagrange error formula then? All right. Let's go ahead and continue on. We saw last time how our rates of change, right, differ depending upon what family of function we're looking at. We added factorial to the list, and what I wanted you to get out of our very brief discussion last time, and it'll help us more as we deal with convergence, is that factorial growth now will outstrip even exponential growth so long as we're looking in the long term as n goes to infinity. And so what I wanted you to get out of our very brief discussion is there's a new top dog in town. Yes, that's right. Factorial now is the winner, chicken dinner, in terms of rates of change and growth as n goes to infinity. Factorial growth will outstrip even exponential growth as we can look at our increasing rates of growth as n goes to infinity. Factorial is the winner. Very efficient in our discussion today. All right, so we already know a lot about convergence, particularly with geometric series. Which series converges and which diverges, why? Go ahead and quietly tell your partner, and I'm going to have you share for all of our YouTube audience in just a minute. So go ahead and decide. Okay, enough talk. Now we eat. Which one converges and which one diverges? Why? Emily and Riley?
The first one converges because r is less than 1, and the second one diverges because r is greater than 1.
Absolutely. Raise your hand if you have the same thing. First converges. Good. Second diverges. Yes, because our geometric series with ratio r less than 1 is guaranteed to converge versus geometric series with r greater than 1 is going to diverge. So either both geometric series, but when r is less than 1, in fact we could do the absolute value of r is less than 1, then our series converges. If r is greater than or equal to 1, then our series diverges. Well, this relatively simple, test and fact is now going to become the basis for a lot of our power series tests, We'll be able to tell whether or not a given series converges or diverges, right? If we can reinterpret it in a geometric way with our ratio r, and if we can make that ratio r less than 1, we know that we're guaranteed to converge for the series. All right, so what about power series with variables and x's and not just n's, right? Not just constants. In its function representation, this parent power series is what? Right? What would this be in its function representation? This is from our old table. Our very first one. What would that look like with x's?
1 over 1 minus x.
1 over 1 minus x. And this should look very familiar, right? This should look like your geometric formula sum, right, of an infinite series, which is given by first term a over 1 minus r, where r is the ratio of my geometric series. It's just that now my first term is 1. There you go, for that one. And my ratio is what? Well, my ratio is x. And so where does this converge? Well, this converges when the absolute value of, now my ratio, right, symbolically is x, is strictly less than 1. So converges when x is less than 1. We will refer to this as the radius of convergence. So the radius of convergence here, r is 1. Versus the interval of convergence. Right? The interval of convergence would then be getting rid of the absolute value and writing as an interval. So we had a little refresher last time. We got rid of the bars by setting this equal, or putting this in between the opposite of this and the positive of this. And so to get rid of the bars, we rewrite as -1 is less than x is less than 1. My interval of convergence would then be -1 to 1. We saw that graphically in our activities earlier when we were generating our parent function for the power series. All right, so now equipped with our new terminology, we've got radius of convergence and interval of convergence for our parent power series. What about some other power series? Like the sum from 0 to infinity of 2x minus 3 to the n, right? What would be the interval of convergence for this? Well, if we can recognize that as our parent power function with a simple substitution, then what's the ratio, right? What's the ratio from this power series? Yeah, and so all we need to do to find the interval of convergence, right? We know that this is a power series with r equal to 2x minus 3. So it converges when the magnitude of 2x minus 3 is less than 1. And depending upon how you'd like to simplify that, we could factor out a 2, bring that 2 out front of my absolute value bars as a positive 2, and divide to get my radius of convergence. But since we're asked to find the interval, we may as well go ahead and break up the bars and go all the way. So my interval of convergence is given when -1 is less than 2x minus 3 is less than 1. Adding 3 to all 3 columns produces 2 is less than 2x is less than 4, which means that x must be in between what and what? Looks like 1 and 2, yes? So my interval of convergence is 1 to 2. what would my radius of convergence R be? Right, what would my radius of convergence R be? It would have to be 1/2 then. Do you guys see that? So my radius of convergence is the distance, right? The distance between the center x value and the endpoints. So my radius of convergence, because some of your directions say find the radius of convergence versus find the interval of convergence. You see the difference? You can go back and find the radius by factoring out a 2, and then it would be x minus 3/2. And then dividing by 2, and you get your x coefficient of 1 inside the bar is equal to or less than 1/2, telling you your R value is 1/2. Okay, so I'm feeling pretty good about that, except that I don't recognize that second one. I don't recognize that second one as a direct substitution in my parent power series. But I'm hoping that you recognize that, right? What is the series? What does the series represent in the second one? You guys recognize it? Yes, if you needed to expand it, you certainly could, but we do need to commit these to memory. And so this, right, this second one actually represents sine of x. And while this first power series only converges when x is between 1 and 2, when does the Maclaurin series for sine of x converge? Well, we only, right, went through inspection, but we saw all the way through what? We did like to the 11th partial sum, didn't we? Didn't we do like the x11th on the calculator? And that was our prepare to be amazed, right, moment. And it was awesome watching more and more waves, right, be traced out by my polynomial approximation. We can continue adding higher and higher order Taylor polynomials, right, and keep going to higher degree terms. It turns out that this converges for all x. So this converges for all x. So the interval of convergence will be negative infinity to infinity. That's pretty cool. What about the representation for the third one? All right, which one is that? Sophia? You recognize that? No? You can look at your page. The next page I'm going to have you guys look at 499 anyhow. For this one? Let's see. If we were to expand this out, let's plug in 0.
It's cosine.
It's cosine, yeah. So we get 1, 0, 0. So I get 1, and then I get the minus, and then I get the x squared over 2. So this is cosine of x. And we can do the same thing with our partial sums that we did, and that was the last one in our familiar functions. Introduction to Taylor polynomials. Or introduction to Taylor series rather, and our interval of convergence for cosine of x ends up being all reals as well. That's pretty cool. Awesome. And what about this? Oh gosh. Anybody recognize this one? What's this, Tyler? Yeah, this represents e to the x. In fact, if I were to expand this, I would get 0 in for n, gives me 1 over 0 factorial is still 1, so I get 1 plus, increment my counter by 1, x to the first over 1 factorial is 1, plus x squared over 2 factorial, plus and in its infinite form, the series is equal to e to the x. One thing that we'll use in our tests, and I want you to recognize, is the value of this series when x equals 1. What if we were to replace every x in this Taylor series expansion with the value 1? Could we figure out the sum, right, the infinite sum that this series represents? Yeah, what is it? we could put in the x right there just as well as putting in the x right here, like you did for Bellwork number 1. Guess what? 1 plus 1 plus 1/2 plus 1/6 plus this equals the number e. I'm going to just go ahead and put that in brackets right here because this is kind of an aside, but it's an important aside. As we continue to recognize these power series and their representations. So through substitution, we can see that easily. If we just put in 1 for x, then when we put in 1 for x, then it equals e, right? But we'll use this in some of our convergence tests later. All right, so everybody, I want you to go ahead and check out your 499, your intervals of convergence for the familiar functions. We know that term-by-term integration, term-by-term differentiation preserves our interval of convergence as we go down the ladder or up the ladder. Our radius of convergence is preserved. We will have to start checking our endpoints. And so what we're going to include in the next 2 days is now checking the endpoints on our intervals of convergence. But for now, we're good finding the radius of convergence, and from that, the interval. Cool. All right, so you guys found them. We've got the ln of 1 plus x. We've got the tangent, inverse tangent one, and so we've got a fair number of familiar ones. All right, so what about this new series? Can we tell whether or not it converges or diverges? Does this match any of your familiar functions from your page 499? Well, does it match exactly any of them? No, it doesn't. But it's similar, right? What does this resemble? Yeah, it's close to our e to the x function representation, isn't it? Right? In fact, e to the x is given by, what do we decide? E to the x is given by the sum from n equals 0 to infinity of what? What's our e to the x? Courtney?
That's the
And that, right, represents e to the x. Okay, so we're not asked to determine the infinite series, that is the sum of all those infinite terms. We're just asked if this converges or diverges, and can we tell? Why don't you go ahead and talk with your partner and make a prediction whether or not this converges or diverges. What do you think and why? Okay, so who's willing to share what they came up with? Do they think it converges or diverges? Tyler?
So because e to the x converges, all this is doing is making the denominator bigger, so it's going to converge as well.
So we know that e to the x, right, in the series, its Taylor series converges for all real x, right? It converges, even if it didn't converge for all real x, but just had an interval like -1 to 1 from our original parent. Tyler's reasoning that this new function, which is similar then, has a denominator which is now larger than this, ensuring that my terms will be smaller as n goes to infinity, so I should expect to converge as well, right? We saw with our geometric series first, in our convergence, if we had a smaller ratio r, then we would converge. And so Tyler's expanding that reasoning to include a greater denominator would make for smaller terms as well, so it should converge. Yes, in fact, that's going to be the nature of the direct comparison test, our first test for convergence. And so if we have the sum, and we'll make these infinite sums, I just didn't have it when I was at home typing. I didn't have the math tools. So we'll go ahead and let these be infinite sums. So if this series, right, the infinite sum of a sub n is less than or equal to the series given by b sub n, generalized term, if a is less than b for all n bigger than some positive integer n, then, and we know that b sub n converges, the series b sub n converges, then a sub n also converges. In other words, if a sub n has smaller terms, as is the case with this green series, has smaller magnitude terms than this e to the x, and e to the x converges, then by direct comparison, this must also converge because it's bounded above by a convergence series. Great. Similarly, if we know that the series given by the sum of C sub n diverges, and our series that we're asking about, A sub n, is greater than our divergent series C sub n, then we know that A sub n must also diverge. In other words, if my series I'm investigating is greater than, right, above a divergent series, then we know that it must also diverge because it's going to be greater than my divergent series. Cool. So the direct comparison test is pretty simple. If we can find, right, if we can find a series to compare with. And so let's let this one be A. So if we let A sub n equal this one, and this is forever less than or equal to the series given by B, which is n equals 0 to infinity of x to the n over n factorial equals e to the x, which converges. So our series must also converge by direct comparison. Cool. So if we can find a series to compare with, right, then we'll be able to tell whether or not a new series converges or diverges. But we need some more series for comparison. So I want you to consider this classic series. That is the sum from 1 to infinity of 1 over n squared. Right? And so let's go ahead and consider the first two terms as if we expanded. So let's consider the sum from 1 to infinity of 1 over n squared. When n equals 1, my first term would be 1 plus, increment my counter by 1. 1 over 2 squared is 1 fourth plus, increment my counter. 1 over 3 squared is 1 ninth plus, plus generalized term. So the sum of the reciprocal squares. This is a classic series. So the sum of the reciprocal squares. Okay, our job is to figure out whether this converges or diverges. So we can actually think about this problem graphically. If we think about, again, that's not a continuous function, right? Yet. That is a sum of terms, right? Each of which has a value that is finite. We just expanded the first several, and they were what? 1 plus 1 fourth plus 1 ninth plus ... Here, though, I've made the graph of the function f of x given by 1 over x squared, a continuous function, yes, decreasing in nature and approaching 0 as x goes to infinity. What I want to do is compare that partial sums of that series with this continuous function that's defined for all real x. Yes? Okay, so if we consider the area underneath this function as x goes to infinity, and then compare it with the value of that series as n goes to infinity, are there some conclusions we could draw? Well, we know how to handle the area question, don't we? If we start at x equals 1, and set up an integral that would give us the area beneath that function and the x-axis, right, in between x equals 1 and infinity, then we can determine whether or not this function, right, has an area that's bounded. That is, does this area exist? Is it a finite value? And can we compute it? Versus, does it diverge? And the area is infinite. So how do we do that? How do we do this area problem? Well, the same way that we did an area problem back in Calc AB. We set up a definite integral. We just want the integral from 1 to what? Infinity. Of 1 over x squared with respect to x. Now that we're in BC, we have the tools to handle that. What do? Well, we investigate this improper integral using limits, right? Our tool from day 1 back in AB is now coming back to us. We can rewrite this now as a limit as b goes to infinity of the integral from 1 to b. We know how to handle the integral from 1 to b of 1 over x squared dx. And that equals, the limit as b goes to infinity of an antiderivative for 1 over x squared. Any antiderivative. What's that? Well, how about opposite of 1 over x evaluated from 1 to b. This, in turn, is given by the limit as b goes to infinity of evaluate my antiderivative at the upper minus evaluate at the lower. So this becomes negative 1 over b minus a negative 1 over 1. Bless you.
Thank you.
Can we do that? You bet your boots. As b goes to infinity, what happens to this fraction? Goes to 0. This means that, right, if this improper integral equals a finite value, a constant, in this case 1, then the integral converges and the area is finite. In fact, it equals 1. So the integral converges and the area equals 1. Okay. We have yet to make a connection with the series, however, and this continuous function for all reactions. So what we're going to do is put this on the back burner and consider this next one, and then we're going to go back and make our final connection. So let's do the same thing, but now let's do it for the harmonic series. This is classic series, super important. The harmonic series that we're going to come back to time and time again. It's, well, the sum of the reciprocal integers, yes? If we were to expand this, right, we get, when n equals 1, I get first term 1, plus 1/2, plus 1/3, plus 1/4, yes? Plus our generalized nth term, okay? So this is called the harmonic series, and this is very famous. Let's go about it the same way. That is to say, our series is a collection of finite values added together, right? Our graph, however, of f of x equals 1 over x, is what I used in the emulator here, is a continuous function defined for all real x inputs. If we were to start at x equals 1, and again, to consider my area case, we could use improper integrals to see if this area is bounded, is finite and exists, or if it's infinite and we can't calculate. So what will we do? Well, we'll do the same thing. I still want this. All right, so let's our area is given by a definite integral, in this case 1 to infinity, of 1 over x dx. And in this case, this is given by the limit as b goes to infinity of the integral from 1 to b of 1 over x with respect to x. And this equals, we'll go gadget, the limit as b goes to infinity of antiderivative. Can we do that? Yeah, what's the antiderivative for 1 over x? Ln of absolute value of x evaluated from 1 to b. And that equals the limit as b goes to infinity of ln of absolute value of b, which is positive because b is going to positive infinity, minus ln of absolute value of 1 is just 1. So we don't need our bars actually. But we can certainly leave them. And as b goes to infinity, what happens to the natural log of b? Right? As b goes to infinity, what happens to ln of b? It goes to infinity, right? It becomes infinite. And so, because this does not equal a finite value, the way that our previous 1 over n squared function, 1 over x squared, right, equaled a finite value, this integral diverges and the area is infinite. We can't calculate. So you guys remembering the improper integrals? Now this is like a couple units back, but you remember how to use it? Okay. So we actually don't need them so much right now, but what I want you to do now is go to the graphs. We're going to now make a connection between the terms of my series geometrically and this picture. We're adding up term values, right? Let's consider those term values to themselves be rectangles. Rectangles with the area that's equal to the magnitude of the term. So let's go to this first term. The first term is 1. Could I draw a rectangle that represents an area of 1? Well, yeah, if I made these are all by 1s, but if I drew my rectangle like this, yes, that first rectangle is the first term. And if I drew my next rectangle to represent an area of 1/4, it would have base of 1, and its height would be, well, gosh darn it, what's that function value right there? When x equals 2, what's the value of this function? 1/4. 1/4 times base 1 equals an area that's equal to the magnitude of that second term. 1/4. Next, when x equals 3, the value of this function is 1/9 multiplied by 1, the width of that rectangle, gives us an area that's equal to this third term's magnitude, 1/9. You guys see that? Okay. Let's do the same thing for our harmonic series. Can I draw our area of a rectangle equal to the first term, 1? Well, absolutely. That first term, 1, has height 1, width 1, but now I draw the second one as 1/2, so I do this. So now my rectangles are over here, though. My second rectangle, x equals 2, produces the function value 1/2, which corresponds exactly to my second term, times a width of 1, and 1/3 would be right here. And you guessed it, 1/4 would be right here. How do these pictures help us determine convergence versus divergence of the series, that is, those terms that are being added together, versus the graph? Well, we just saw how this area was finite, right? And the term values are all bounded beneath my curve, except for this first one, which is 1, which is a finite value itself, right? In fact, 1 plus whatever this converges to guarantees the maximum for my series then must be 2, because 1 plus 1 is 2. But look, my term values are all contained beneath my function. And my function has an area that is finite and exists. Therefore, that series must converge, right, to a finite value. So, again, by the idea of comparison, where the area, my terms are bounded by, right, the area on this continuous function, that series must converge in the same way that this, right, area is infinite, and yet my term values are greater than this infinite area, ensuring that that series does what? Diverges. And so this famous harmonic series diverges. Okay, so 1 over n diverges. 1 over n squares, unsquared, converges. And so we'll be returning to that as well. Emily?
Why in the first graph, like the first and second, they both have 1 as their first term,
Yes?
but the rectangles are in different locations?
Absolutely. So how come we're over here for our first one? Well, we wanted to make our term consecutive. I wanted to make my terms consecutive. Consider the value of the second term. The value of the second term is 1/4. Where would I have to draw my rectangle in order to have an area that represents the second term's magnitude 1/4? Well, I have to draw my rectangle when the height of it is 1/4, and that happens when x equals... Oh, you're saying why can't I draw it over this way?
Well, I'm just confused why the one rectangle is here and then the other one rectangle is here.
Oh, I put them there purposefully so we could show how this is bounded below by a convergent integral, ensuring that my series will also converge. We're beneath, like Tyler was saying with the n plus 1 only made the denominator larger, so we were less than a known convergent series. Now my terms are less than the area of a known converging integral, if I draw them like this. But this one's over here, right? But it's 1, which is finite. So as long as we can say that this is bounded by a finite number, and this is a finite number, 1, then we know this series must converge, because it's finite.
But like you could do the same thing for the second one. That's the first rectangle.
Oh, yes, but by drawing it like this, we are showing that it's greater than forever this divergent series, because we're trying to show that our thing is greater than a known thing that diverges.
Yeah, I know. I'm just
Basically,
confused.
you have to draw the graph after you know if it converges or diverges.
Yes,
You can't just like
Yeah,
pick
just
the
draw
right-
Draw it on your own.
correct. We could have drawn that on the other way and still have the same heights.
Yeah.
I totally agree with you. But what we're trying to do is show how we know how to do the integral.
Okay.
And the integral diverges. So if we pick the integral to diverge and we draw the picture to show that it's forever greater than it, then we've just proven that it diverges. Versus the other way, we wanted to make it so it's underneath it, because we know the integral converges. You see?
Yeah.
So it's all about the comparisons. Cool. I thought it was cool. All right, so the integral test is really not today's stuff. It's really for next time, but we've just used it. And so it bears pointing out. If, right, a sequence, if a sub n is a sequence of positive terms, and I can represent a sub n by f of n, a continuous function like we just did, that's positive and decreasing function for all n greater than some positive integer n, then the series and the integral both converge or both diverge. And that was our point there, is that we were trying to show that these both diverge for the harmonic, and they both converge for this. And so, yeah, the rectangles were an after the fact, after we already knew that the integral converged or diverged, because we were trying to use comparison. All right, and we're scooching right over that into direct comparison. It's nice, but it only works for series that are positive with their terms. No problem. we can apply our test to the sum of the absolute value of term number a sub n or term value a sub n, which certainly has no negative terms. And this ends up being more powerful if the absolute value converges, if the absolute value of the series converges, then the regular series converges, and we say that it converges absolutely. If a series converges absolutely, then that automatically converges. That is, if the series of the absolute value of the terms converges, then the series that's the original one also converges. Okay, so does the series converge or diverge? Well, are those terms all positive? Well, no. We know that cosine, right, oscillates between positive 1 and negative 1. And so we can't do the direct comparison, but we can consider absolute convergence by simply considering the absolute value of the original. And if the series with the absolute value of the terms converges, then the original one converges as well. And so let's go ahead and investigate this. Notice how the n factorial is just a constant, and the n is just a constant, and they're positive integers for our series index. So the absolute value only needs to apply on the cosine x term, because n is always positive. Or I should say non-negative. And what do we know about cosine of x? Well, cosine of x is always, right, in between positive 1 and negative 1. And if we're doing the absolute value of that, then that's always between 0 and 1, right? And so this particular series is... Oh, get your party started. Wow, that's cool. We know that this is forever less than or equal to just 1 to the n over n factorial. And 1 to the n is just 1. And this should look familiar. Gosh, it's so darn close. It was our little aside. You guys see this? And so isn't this 1 plus 1/2 plus 1/6 plus? Yes? Do you guys see it? What does that equal? E. And so, since a finite number, right? So since that series is less than or equal to forever a known convergent series, right? Then it must also converge by direct comparison. So I'm going to say which converges to E. Since our original was everywhere less than or equal to this known convergent series, then the original converges by direct comparison. Comparison. Okay, so now is the time where we decide that we're going to have to do the ratio test, the all-important, all-powerful ratio test, which is the main topic for today. Next time. What we're going to focus on is our direct comparison, because I feel like we've made a good case for that. So does the series converge or diverge? Does the series converge or diverge? Well, I've never seen this series before, right? But we could make a case for convergence or divergence based on our discussion today. So I'm going to go ahead and pause the recording, and you guys are going to decide. I'm going to modify OTL. All right, so who's going to share their reasoning? Does it converge or diverge?
Converge.
Everybody ready? Anyone wants to? Anyone want it? Want to flip? You just said?
Yeah.
Yes? Okay, so what do you compare it to? What are you going to compare it to?
I don't know.
That's a great question. So we want to look at it, right? And we're trying to see how this compares with the convergent or divergent known series. So I, right, have a limited library of series that we know about, but this sure looks like a geometric series. A geometric series with, well, notice how this just made the denominator bigger, like Tyler was saying with the n plus 1 factorial, going from the known n factorial, made the denominator bigger, and then it converged. If I were to just cover up that plus 2 for a minute, then that would be 1 over 3 to the n is a geometric series with ratio 1/3 to the n. And I know that if my ratio r is 1/3, does the series converge or diverge? Converge. And so I'm going to purposely choose to compare this with my geometric series with ratio r equals 1/3. And can show then that this will, because the denominator increased by 2, will forever be less than or equal to my known series that converges by geometric r less than 1. Therefore, this one must also converge. So let's go ahead and do that. So this is forever less than or equal to the series given by n equals 0 to infinity of, and I'll write it twice. Does that help to rewrite it twice? Now, does everybody recognize this? So this is geometric with ratio r equals 1/3, which is less than 1, so therefore it converges, right? So my original must converge by direct comparison. So this is tricky because you have to find something to compare it to. Now you're going to use your table for the first ones on your homework. You're going to look at page 499. You're going to try and see if you can manipulate it to make it look like something you know, and you're going to use other stuff. All right, so what are we going to say? This is geometric with r equals 1/3 less than 1, so converges. Thus, original converges by direct comparison. Okay, so what are we going to do for closure? We're not going to get to ratio, super powerful test, but what we can do is get to this, which you'll need for some of your convergence, divergence in your OTL, and comparison test, which is perfect. So 1 and 2 are your closure today, and it'll work out perfect. Okay, so today is just closure 1 and 2. In order for a series to converge, in fact, this is the first thing that you should consider. What has to be true about the nth term, Riley?
The nth term must approach 0.
Absolutely. As n goes to infinity, the nth term must equal 0, right? Now, just because the nth term equals 0 doesn't mean the series converges, but in order to converge, then the nth term must go to 0, right? We saw the harmonic series 1 over n. The nth term does approach 0, and yet it's a divergent series. State the comparison test for convergence and divergence of a generalized series, sum of base of n. So basically, if my series is forever less than or equal to some known converging series B sub n, then A sub n converges also. versus if my series investigating A sub n is greater than or equal to some known diverging series, call it sum of C, then A sub n must also diverge. Oh, you guys doing okay? All right. Have a great day. It's going to be a short assignment, and then we'll look at ratio tests next time.